So, welcome again to our Physics Form 4. Mr. Cabrera here, and today we are just going to do a short recap of, some of the things that you already know, but in the interest of, moving forward, we should, remember these little concepts so that we can continue. I know we've had a bit of a break over the COVID period, and now that we are back in school, a little refresher could help. So today we're just going to look at a couple of simple things, and the first thing I'm going to start with is that of gravity. So gravity, as you know, was credited to Sir Isaac Newton, and a lot of people say, well, he discovered gravity when an apple fell on his head. That's not entirely true. He was a philosopher and scientist and mathematician, and I believe, as legend goes, when the apple did fall on his head, he started to wonder why it fell on his head, and as a result, he came up with that theory that we basically use today, and that is, of course, gravity. Now, gravity at the CSEC level is taken to have a value of 10 meters per second squared. So that's here, 10 meters per second squared. Now I like to think about this minus sign here as meaning per, right? 10 meters per second squared. Or it can also mean 10 newtons per kilogram. Now first of all, gravity is a force, right? And if you look at the second unit, 10 newtons per kilogram, on Earth, gravity acts on all masses with a force of 10 newtons per kilogram, meaning for every kilogram of mass that you have, you will receive approximately 10 newtons of gravitational force. And this goes for solids, liquids, and gases. Now the thing is, gravity again is a force, right? It is actually the force acting on your mass. And let's recap what mass is. Mass, on the other hand, is the amount of matter that something is made up of. So let's just say, for example, something has a mass of 50 kilograms. Then its weight would be 50 multiplied by 10 newtons per kilogram, which is gravity, and that will give us a weight of 500 newtons. So if you have a mass of 50 kg and gravity gives you 10 newtons of force per kilogram, then 50 by 10 is 500 newtons. Now let's take a look at the unit, and of course the unit of weight, right? And gravity is what gives objects their weight, right? Is the Newton, right? Weight is the amount of gravitational force acting on a mass. So let's look at how we derive that unit, the Newton. So first of all, the formula for gravity is W, weight, is equal to the mass multiplied by gravity, right? Mass, of course, the standard SI unit of mass is the kilogram, and we're using in this case the unit for gravity is the Newton per kilogram. And if we were to, of course, this is kilogram to the minus 1, the index is minus 1, and the index here is plus 1, and since they have the same base, kilogram, once we are multiplying, right, we add the indices, right, and that's how we end up with Newton by itself. They basically cancel themselves off. Or the other unit, which is the same, right, is the kilogram meters per second squared. Now, meters per second squared is acceleration, and often gravity is referred to as, when something is free falling, for example, right, it's called acceleration due to gravity. So gravity accelerates everything towards the Earth. So if something is going up while gravity is pulling on it, gravity is slowing it down. So if you were to throw a ball upwards, for example, it goes up, but it decelerates, it slows down because gravity is pulling it at at acceleration due to gravity value of 10 meters per second squared, right? So these are the units, and it's kilogram meters per second squared or Newton, and these two units, of course, are the same. And when we move on to Newton's laws, we will prove that these two units are the same. So at this stage, let's recap. Gravity is taken at the c-sec level to be a value of 10 meters per second squared or 10 newtons per kilogram. Weight is, of course, the amount of gravitational force acting on your mass. Your mass is the amount of matter that a substance is made up of, whether it's solid, liquid, or gas, right? And the formula for calculating the weight, of course being the force of gravity acting on your mass, is W is equal to mass multiplied by gravity. Weight is equal to mass multiplied by gravity. All right. Another thing that we want to recap today is that of density. And density is defined as the mass per unit volume of a substance, right? It's how much mass, how much matter can fit into a particular volume or space. Volume, of course, being the amount of space that an object or a substance occupies, right? And not to be confused with, a lot of people think it's capacity, right? It's the amount of space that something occupies, a substance occupies. Of course, if you look at the formula, it's the symbol for density is this symbol here, and that symbol, of course, is rho, R-H-O, rho, and rho is mass divided by volume. Density is mass divided by volume. If we were to look at the units, the unit of mass is the kilogram, and the unit of volume is the cubic meter or the meter cube. So therefore, if we were to write this in simplest form, it would look like this. Kilogram, if you were to bring this meter cube to the top, of course it's a positive 3 at the bottom here in the denominator, but when you bring it up towards the numerator, the positive sign must change to a negative. As I told you, I like to think of this as per, so you read this as kilogram per meter cube. Okay, so that is density in a nutshell. And then, of course, we are familiar with relative density. Relative density is a ratio or a comparison of the density of a substance to some standard density. That's what you would most likely see in a textbook. At the c-sec level, right, we compare the density of the substance to the density of water. Now, the reason why we do that is because the density of water, of pure water, happens to be a pretty, decent value to work with. All right, the density of water is 1,000 kilograms per meter cube. All right, and that's a pretty nice value to work with. So this is the density of water right here. Right, now relative density, right, is the density of the substance compared to the density of water, or the ratio of the density of the substance to the density of water. It is a comparison, and because it's a ratio or a comparison, it does not have any units, right? But it's not enough to say that because it's a ratio or comparison, it doesn't have any units. We can also prove that these units basically divide each other out from the formula, because the density of the substance is in kilograms per meter cube, whereas the density of the water is in kilograms per meter cube. And if we were to divide them, they divide themselves out. So relative density is the density of a substance compared to that of the density of water. So let's just say, for argument's sake, we have a substance that has a density of 5,000 kilograms per meter cube. Right? Now the density of water is 1,000 kilograms per meter cube. That means that the substance that we are talking about is 5 times denser than that of water. Therefore, its relative density is 5. If, however, we had a substance that had a relative density, a density rather, of 500 kilograms per meter cube, right? The density of water, of course, is 1,000. Then if you were to divide 500 by 1,000, you would get 0.5. So the relative density in this case is 0.5. So from the moment I say something has a relative density of 2, you should be thinking it's twice as dense as water. If it has a relative density of 0.75, then it is 0.75, of course, is 3/4, right? In terms of a fraction, it will be 3/4 of the density of water. So it should be 3/4 of 1,000 is 750. So basically, if you have the relative density, if you are given the relative density of a substance, all you have to do is multiply by the density of water, and you would get the actual density of the substance. So if something has a relative density of 4.5, then 4.5 by 1,000 is 4,500. So the density of the substance is 4,500 kilograms per meter cube. So I hope this little refresher, kind of clears up some of the, little clutter, and maybe, reminds us a little bit of these little things that we've done, because we need to know and understand these things as we move forward. So I'll see you in another video. Thank you.